Hello, my name is Kelsey McDonough, and I am a hydrologic engineer with VO & Associates. Today, I'll be talking with you about operational modeling of post-fire and geologically prone landslide and flooding potential in the Boulder foothills. If many of you have been reading the news lately, you'll know that post-wildfire landslides and floods are on the rise. Many of these headlines are probably not new to most of you. In Colorado, Interstate 70 through Glenwood Canyon has been repeatedly closed this summer due to intense rainfall over the adjacent Grizzly Fire burn scar. It is now closed indefinitely as crews work to dig out the highway from repeated landslides that have resulted from intense precipitation in the area. Colorado is not the only state having to deal with these issues. Many others in the West, including California and Oregon, are dealing with similar post-fire landslide and flooding issues as well. 2020 brought those of us in Colorado several large wildfires, particularly in the Front Range, with Cameron Peak, Calwood, and the Left-Hand fires, and the massive East Troublesome Fire on the western slope of Rocky Mountain National Park. While fires alone can be equally destructive, both ecologically and for human infrastructure alike, the post-fire flood and landslide impacts can be just as horrific and damaging. We often don't hear about post-fire landslides and floods because they often occur far into the wilderness, in places where people are not typically impacted. However, as human population centers expand and the intensity and area covered by these wildfires increases all over the world, it is only natural that we will have to begin to deal with these post-wildfire flood and landslide impacts to infrastructure and to population centers, as we have seen in the Interstate 70 corridor in Glenwood Canyon this summer. You may be sitting there wondering, so what is the link between wildfires and floods or landslides? Well, following a fire, the affected area is fundamentally changed for at least 1 to 5 years. This not only impacts the ecology of the area, but the hydrological response of the region as well. Depending on the burn intensity of the fire, the vegetation is either degraded or lost. If the fire is really intense and very, very hot, no vegetation will return the following year, naturally. Soil sealing or hydrophobicity will also occur due to fundamental changes to the soil structure by the fire itself. Together, these two changes, loss of vegetation and hydrophobicity, impacts the following hydrological processes: decreased initial abstraction, decreased infiltration, increased erosion, and accelerated routing of water, which manifests itself in terms of decreased water storage, increased overland flow runoff, degraded water quality, and loss of soil structure. These fundamental physiological changes in the landscape work together to enhance both the landslide and flood risk in a post-fire environment. These changes were observed in the Calwood burn area this spring following the 2020 fire. The images here show increased erosion of the landscape, which results in both a mud flow here and a debris flow here in this area. You can see this particularly manifested with the different changes in color of the river here, where it's much darker here on the left and much lighter here on the right, showing that there's significant mud flows occurring and being moved by the river here on the left. The interesting thing with post-fire hydrology is that compared to pre-fire conditions, where a specific rainfall intensity or depth that would have previously caused no issues or problems in terms of flooding or landslide and debris flows will now cause a whole headache of problems in the post-fire environment. You'll begin to witness new behavior in the streamflow hydrograph in terms of response to a storm that previously didn't cause flooding or landslide issues. However, exactly how these fundamental physiological changes will impact hydrology is unknown. It varies from burn scar to burn scar. It will change over time as vegetation reestablishes and the ecosystem begins to heal. So for example, this is a screenshot from our View Information platform, which is an online monitoring platform. Behind here, this shows the gauge-adjusted radar rainfall over the Calwood burn area in June for a particular storm event that occurred. And this is a hydrograph, a screenshot of a hydrograph in the Upper Gear Canyon Heil Ranch confluence. And what we'll see here is that the stream flow hydrograph response will be much bigger now post-fire here than what we saw previously before the fire occurred. Over time, how this hydrograph responds to this exact same rainfall event will change as vegetation begins to reestablish, soil structure recovers, and different ecological changes occur as the entire burn scar begins to heal. Because ecological behaviors are so unknown post-fire, there's a serious need for real-time modeling of post-fire hydrological impacts, particularly with respect to landslides and floods, so that we can begin to answer these questions. How does the hydrological response of an area change post-fire? What depth and duration of storm will trigger a flood or landslide event? What is the emergency response lead time for road closures or enacting other safety measures? And what are the potential impacts to infrastructure from post-fire floods or landslides? We at View & Associates have been involved with real-time operational modeling in the 4 Mile Creek burn area since July 2011. Rainfall-based alert notifications for flooding have been in place since that time for operational emergency management for folks at the Mile High Flood District. This is screenshots of our modeling platform, where they've been able to monitor different rainfall events as it moves over the 4 Mile Creek burn area since 2011. This is an example of the type of notifications that Mile High Flood District has been receiving since 2011. Alert notifications based off of current and forecast rainfall, with both observed flow from USGS and predicted flow from our calibrated and validated 4 Mile Creek VFlow model. We wanted to build upon the modeling capabilities offered in the 4 Mile Creek post-fire modeling work to develop a post-fire flood and landslide prediction model with our Hydrologic Model VFlow for the Calwood burn scar. VFlow is a gridded, physics-based distributed hydrologic model that was developed at View & Associates in 2011. As a physics-based distributed model, VFlow solves the governing equations of conservation of mass, momentum, and energy using the kinematic wave solution for routing. The kinematic wave analogy is solved over a spatially variable surface using finite elements. This results in the ability to produce a hydrograph at any location throughout the drainage network based upon rainfall intensity. The recent addition of the subsurface regime in VFlow, with the equations shown here, enabled the computation of a secondary runoff component in addition to the surface-only runoff model. The subsurface runoff process accurately tracks and calculates subsurface runoff between grid cells in the model, thus accurately accounting for soil moisture and groundwater fluxes. More importantly, the subsurface runoff regime adds the ability for continuous soil moisture monitoring in real time for mountainous watersheds and burn scars. VFlow has been previously applied to a variety of hydrologic applications using both the previous surface-only runoff mechanism and the new surface plus subsurface runoff regime. Both operationally and for post-event analysis, VFlow has been utilized for a number of applications, including hydrologic and watershed assessment, real-time flood prediction, operational emergency management decisions, collection systems management, stormwater management, reservoir operations, and more. For the Calwood burn area, it was necessary to set up a hydrologic model to simulate flow over an area called Hogback Ridge, which is located within the burn area. The goal of this model, using both the new subsurface regime in addition to the surface-only capability, was to accurately predict landslide occurrence using rainfall intensity with gauge-adjusted radar rainfall, or GAR, as input into the model. Since there is no USGS observed streamflow gauging stations within the Hogback Ridge area, the 4 Mile Creek model that I mentioned previously underwent additional calibration and validation to account for recent events in the notable 2013 Front Range flood, to update the model and then apply the model parameters from the 4 Mile Creek model to the Hogback Ridge model. Key hydrological parameters, including Manning's roughness and hydraulic conductivity, were taken from the 4 Mile Creek model and applied to the Hogback Ridge model in lieu of calibration. With the subsurface runoff regime enabled, continuous soil moisture tracking and thus landslide prediction was possible. And I'll go into that and how we went about that in the next couple of slides. So to quickly just reiterate the model development for Hogback Ridge, we recalibrated the 4 Mile Creek V-flow model using subsurface parameters since the previous 4 Mile Creek model was just a surface-only hydrologic model. You can see the observed changes in calibration and validation from surface only, shown in blue, to subsurface included, shown in orange, in these 2 hydrographs here on the right. The calibrated subsurface parameters and surface parameters were then applied to the Hogback Ridge model, which was used for flood and landslide prediction within the Calwood burn scar. The subsurface parameters, including bulk drainage, for calibration and validation of 4 Mile Creek were estimated from subsurface seasonal parameters during the 2013 snowmelt season. Estimation of these parameters enabled the use of the subsurface routine and subsequent accounting of soil moisture and groundwater return flows. Historical landslides within the Hogback Ridge area from the 2013 Front Range flood were then analyzed to identify a maximum soil moisture threshold for areas that experienced a landslide. This here image on the right shows a screenshot of the hydrologic model over Hogback Ridge. At every single pixel within the model domain, soil moisture is being simulated, as you can see here in these figures on the left. We were able to see which areas that underwent a historic landslide experienced very high soil moisture saturation values, and were able to extract a soil moisture saturation threshold from those historical landslide simulations. Using all of that historical information, qualifications for a landslide within the Hogback Ridge area were established to form a landslide prediction grid. For the model to predict the occurrence of a landslide at a particular pixel, that pixel within the gridded domain had to meet a couple of following conditions. 80% saturation, it had to have at least 40% slopes, and predominantly landslide-prone soils had to be dominant in that pixel, which included the Baller Stony Sandy Loam, the Pinata Rock Outcrop, and the 6 Mile Stony Loam. You can see the V-flow landslide prediction grid here, where the red dots are historical landslides from the 2013 Front Range flood, and the yellow areas are areas that are able to meet these qualifications of having a specific slope, landslide-prone soils, and then at certain times over 80% saturation to show that a landslide could be possible in that area. We validated the landslide prediction grid against historical landslides that occurred in the area during the 2013 Front Range flood. Of all the landslides that occurred in 2013, we correctly forecasted 89% of landslides, although it's important to note that false positives did occur. You can see what this looks like graphically over here on the right, which shows the results from the 2013 Front Range flood. The historical landslides are in red, and the pixels that predicted a landslide are shown in yellow. So once the 4 Mile Creek model was fully calibrated and validated, we took its key validated parameters and applied them to the Hogback Ridge model, and then finished developing the Hogback Ridge model for operational applications. We were able to deploy the Hogback Ridge model to our View Information Platform, or VIP, which is a web-based management platform that enables real-time simulation of the model with operational management applications. Once the model was enabled on VIP for hydrologic simulation in real time, we applied the following thresholds for operational alerts. Using the landslide prediction grid, shown here on the right, an alert would be sent to emergency managers that a landslide was possible once 75% soil saturation was reached in one of the pixels here, shown in yellow. So to reiterate, once one of these grid cells reached a 75% soil saturation, then an email would be sent to the folks at Mile High Flood District that a landslide was possible in that area. Currently, our only capability is to send alerts out via email, but we are in the process of developing a map-based feature for our view information platform that will display the grid cells in real time and be able to indicate which cells have crossed the soil moisture threshold, very similar to what you see here in this image on the right. In practice, our VIP mapping feature looks like this. These two images currently display gauge-adjusted radar rainfall as it moves across the Calwood Burn area on the left and the 4 Mile Creek area on the right. This GAR is projected forward by 1 hour in terms of both speed and direction, otherwise known as our preview product, which is then input into the Hogback Ridge Hydrologic Model to obtain forecast stream flow, stage, flood, and soil moisture, or landslide predictions, by 1 hour into the future. The key advantage of our system is that it uses current rainfall intensity via gauge-adjusted radar rainfall and projects it forward by 1 hour. This system is then fast enough to take that GAR information, input it into a model, the Hogback Ridge model, run it in real time, and then get an estimate of future hydrologic conditions within an area, in the Calwood Burn area in this example. It is fundamentally more useful than post-analysis modeling of a landslide or flood event because emergency managers can take the forecasted hydrologic information and take appropriate actions as necessary to save lives, such as closing roads or evacuating areas if a landslide or flood is predicted to be imminent. As I mentioned earlier, this information is currently sent to emergency managers and first responders in 2 ways: text-based alerts or email alerts, which contains a map of the GAR and the location affected, as you can see here in the image. As I mentioned previously, future developments of our view information platform will include mapping of the landslide prediction grid so that users can log into the view information platform and view the response of the landslide prediction grid in real time as rainfall moves across an area, especially in the Calwood Burn Scar. With that, I'd like to thank you all for your time today, and I'd be happy to answer any questions as time permits. Thank you.